Let me start by reminding you that in higher topological quantum mechanics, we associate to an interval the following object. Where H is Q of G. Now, let us study in higher topological quantum mechanics so-called correlator. So here we have V in that belongs to the functor applied to a point. Here we have V out that also belongs to the functor applied to a point. We divide the interval into subintervals. T1, T2, dot, dot, dots, Tn. So what do we associate to this object? So here there'll be a long formula. I start with V in. And then I have here exponent T1H plus DT1G. Now, what do I associate to the point?
An identity operator?
No, an element. So point, so here I have observable, O1, that belongs to endomorphisms of the space V. And that's why here I write O1. And then I write E T2 H plus DT2G. And then I write O2. And all the way up to V out. So what can I say about this? It is differential form on configuration space. And configuration space is a space of positions of points. So coordinates on configuration space are T1, etc., Tn. So this is the main object. Let me call it star. What is interesting is that object star has several meanings. And interesting things happen when we change one point of view on the object star to another point of view on the object star. Point one. Sometimes object star is an interesting problem okay, sorry, not object star. Object star at a differential. I'm sorry. It is, so since it's differential form, it is instructive to integrate it over configurations. Actually, that's what we do with differential forms. We integrate them over something. And this integral, I will change this, has several meanings. This integral turns out an interesting mathematical object, mathematical number in mathematical application. Second, as we will see in a moment, this integral is a deformation of higher topological quantum mechanics. Third point of view, this integral satisfies interesting quadratic relations. Point number 3 provides relations between mathematical problems in point 1. At the same time, point number 2 says So I will say it in advance. It is a key to mirror formulas. And key to mirror formula says that, so mirror formula say that mathematical numbers of 1 correspond to the formation of topological theory. And what is important is that up to now, we study it in dimension 1, where everything is explicit. However, we will generalize it to real dimension equal to and even to real dimension of the space equals 4 by conjectural equivalence between functorial and Feynman approaches to higher topological quantum fields. Okay, so my goal is to explain these points. Okay? So let me start with the simplest possible example. Suppose I have V1, and here I use what I involved last time, what I defined last time. This differential form corresponding to the cycle C1 and V2, differential form corresponding to the cycle C2. And then I have this differential form. And here I have omega C1 epsilon. Here I have omega C2 epsilon. And I'm integrating over X. And I will take H being Lie derivative, G being operator of contraction with a vector field. And now I would like to integrate over this dt. What does it mean geometrical? I have cycle C1. I have cycle C2. They do not intersect. I am looking for trajectories of the vector field that are starting at C1 and ending on C2 trajectory. And I do not care about time. Trajectory moves. Trajectory goes from C1 to C2. Saying that I don't care about the time actually means that I'm integrating over R plus. Anytime. Let me compare it with the easy problem. Here I'll write very similar integral. But without dt. You see the difference is that here I do not have an integral. It is a function of t. One can show that f of t is actually a constant. So picture is like this. So how can I show it? I take derivative of f of t with respect to t. And here I have this h, e to the th, omega c1 epsilon. Now, h is d of iv. I put it here and integrate by parts. And I get 0. So it's not very interesting. f,
I have
f of t.
two questions.
Yes.
So one is so Q does not have to always be D, right? It can also be different. Or is it just different notation? We can say either Q or D.
So here in this example, Q was D.
Uh-huh. And the second question is, we showed this f of t is actually a constant, but it depends on this C1 and C2.
Of course.
Is this dependence interesting, or
It is just an intersection number of C1 and C2. So it is something relatively easy.
intersection number of C1 and
Of
C2,
cycles C1 and C2.
or of C2 with C1 transported by the time t?
Yes. So we somehow show that they are the same.
Well,
Because
I think
when we transport C say C1 tilde, it's a homotopy. It's actually D of something. That's why I call this easy problem. And such numbers are not very interesting. You will never get a Fields prize for it.
I don't quite understand. Like, I can imagine quite a few contours that do not intersect originally, but do intersect when I transport one of them by t.
It's
Am I
impossible.
imagining something wrong?
Yes, it's impossible. You may just consider example. I gave you a formal proof, but you may also see it with your geometric eye. That's impossible.
Well, just say x is two-dimensional.
Yes.
And the flow of h is something very simple, like just vertical line, vertical flow. I don't know, and I imagine like two circles, and originally they don't intersect, but after I transport one of them by the time t, they do intersect by 2 points. Yeah, something like that.
But intersection should be taken with signs.
Oh.
So here you have contribution +1, and here you have contribution -1.
Is it clear from the integral that these are signed contributions?
Yes. you may check it from the integral that they are signed. Because last time we ended with the statement that Z1 times omega epsilon Z2 is omega associated to intersection. But then you may easily see that here Z2 was considered as oriented. And this orientation is involved in the intersection. So this integral over x is the number of points taken with sign.
So the intersection of two oriented cycles naturally inherits orientation, yes?
Yes, of course. There is orientation everywhere. And cancellation is like dx dy is minus dy dx. I can even draw it. So let this be Z1. So this is a piece of Z2. And here is another piece of Z2. You see, they go in opposite direction.
Yeah, I understand. Thank you.
Okay, so my point is to say that that the easy problem is a problem where you do not have differential form. You have function, and the function is constant. However, integral over r plus of omega, and here I put cycles, c2 epsilon e to the, let me be very explicit here, iv dt omega c1 epsilon is a new enumerative problem. In particular, if dimension of x equals 3, and dimension of ci equals 1, we typically have a non-zero answer.
Here we just expanded the exponent, but
Yeah.
something happened with the 1. So via previous,
we integrate over R plus. We integrate one form on the configurations.
yeah. So the integral of that 1
We
is 0
throw
because it's
one
not
away.
a 1 form.
Yes, we integrate over R plus a one form on the configuration space. And the meaning of this number is what I explained. Any trajectory. So it is a new number.
But here, the notion of orientation is kind of preserved because we are only interested in trajectories that go from C1 to C2, not the other way around.
Yes, of
right?
course.
Mm-hmm.
Yes, of course. So, so I kind of explained that the point that we have new numbers. And now I would like to go to the point number 2. And point number 2 is relation between new numbers and deformation theory. In functorial approach to quantum field theory, we observed the deformation of quantum mechanics is h goes from h to phi. And there was a nice formula. It was actually a decomposition. I'm sorry. T tilde H pi T minus T tilde H plus higher terms. Now it is instructive to compare this formula with this formula. And you will see that integrals over configuration space correspond to deformation of H to H plus commutator GO. So phi is just GO. So how to see it? I think what is the best way to see it? Let us have a look at this formula. We expand exponent to get forms on configuration space. And then we will get commutator of G with O. That's how it works. In particular, in the deformed theory, H that was QG or GQ is the same, goes to GQ plus GO. So deformed theory, again, is topological. With a new Q. Q goes to Q plus O. Now, it's interesting to note that we already have seen it in example. Q was D. O was omega, we will take omega on some cycle. So we will have deformation d plus omega epsilon on the cycle. And this is Witten-Novikov deformation. That we have already seen. So interestingly enough, Witten-Novikov deformation correspond to an enumerative problem. We have trajectory, and here we have cycles, omega c1, omega c2, etc. Okay, so here I have C in, here I have C out. So let me write it a bit more formal. Let me introduce generating parameter. Tau I for a set of cycles Ti, such that parity of Ti plus codimension of Ci, and this is actually dimension of omega Ci epsilon equals 1 modulo 2. Let me introduce object O of T. That is sum of I, tau I, omega epsilon Ci. Then deformation d going to d plus O of tau corresponds to generating function for enumerative problems. C1, C2, Cn. in any order. So I compute the number of trajectories passing through these cycles. I call them NC1, Tn, and here I write generating parameters. Let me write it in this way. And I construct this generating function. And this generating function corresponds to, so here I take a sum, to a deformed topological theory. Let me continue. So to make life more interesting, let me outline how people were getting Fields medals based on this set of ideas. Point number one. So I'll outline and I'll explain details tomorrow, okay? Point number one. Consider vector field of the Morse type. So what does it mean? It actually means the following. We already met this vector field before. Maybe I even write this, I call it W. Here W is a function on X. And Gij is a metric on X. Why these vector fields are so special? Because such vector fields do not have limiting cycle. So if you don't know what the limiting cycle is, I can just draw you a picture. Trajectory of a vector field can go like this. And this is called a limiting cycle. So Morse vector field have no limiting cycles. Only limiting point. Reason. Consider the derivative of W along the trajectory. dW over dt equals dW over dxi vi of x. However, it equals dW over dxi dW over dxj gij. And this thing is strictly positive. So trajectory cannot make rounds. So limiting cycle is impossible. Well, now we can look for a numerative problem. Here is our manifold X. Here we have fixed point of V Morse. And here we have another fixed point. So what can we study? We may study, it's a thing that Morse did. Number of trajectories going from A to B. Let me call it NAB. In general, it is not a number. They form families. However, Morse proposed to study only isolated trajectory. You see, now I'm outlining the idea, okay? I don't want to go into detail. And also Morse proved several things. N, A, B, N, B, C, sum over B equals to 0. So there is a complex. Spanned by critical points with NAB being a differential. He also showed that this complex is quasi-isomorphic to cohomologies of X. And it is where Morse stopped. However, now we know that Morse theory may be refined, namely, consider new numbers. Number of trajectories going from A to B and passing through cycles. C1, Cn. And this is the picture that we have already met. Sorry. It is a new enumerative problem. Now, it is instructive. Now there are relations between these numbers. Let me write some of these relations. So here are Morse relations. Equal to 0. There are even more interesting relations. Plus, you can interchange 1 and 2, plus later on you will write NAB empty and BC C1 C2. So here is a comma. So there are new numbers and quadratic relation. It turns out that all these relations may be written uniformly as CI1, CIN, tau I1, tau IN. And all these relations have a very simple form. So new numbers correspond to the formation of the Morse complex. And in principle, one may say something about this new number.
I have a
Yes.
I have a question. So on the previous page, the relations for NAB of cycles. For instance, the second and third line. Or, did I miss it, or is it obvious, or are we going to prove it next time, or it can be proved in principle, or?
You see, today I'm going to outline the proof, and next time we will prove it.
Okay.
You see, before I'm going to prove something, I want you to see that it is interesting. Okay? So NABC turns out to be just action of omega C epsilon on cohomology of X associated to points A and B. So it's an old operation. However, NAB C1 C2 is a new operation. And this operation is known in mathematics as Massey operation. Actually, I need to put here, I want to be strict, refined. And and here I need to mention first Fields medal. Rational homotopy type of the manifold is given by its Massey operation. So it's not just cohomology ring. It's higher. So in order to get the homotopy type of a manifold, it's not enough to know cohomology ring. You need to know these higher operations. So we kind of constructed these higher operations, and then it turns out that these higher operations characterize topology of the manifold. And it's a Fields medal to Sullivan for proving it. Okay. But it's only one first Fields medal. Let me tell you about another Fields medal related to this set of problems. Consider variation of the topic. Replace one dimension quantum field theory by two dimensions. Replace equations by holomorphicity equation. Then we will get two-dimensional quantum field theory. In the same style, we will get functional integral of I write it symbolically. To many letters. And here we have similar objects. I'm sorry. And here we put O. Omega 1 at point Z1, O omega n at point Zn. So what are these omegas? So O omega 1 at point Z1 is nothing but omega 1 computed over X that depends on point Z1. And also psi that depends on point Z1. Where this is differential. Now, interestingly enough, configuration space is the space of points on, we consider CP1. Just see the similarity. we generalize like this. And again, we study differential forms on configuration. So how do we get differential forms? We put here analog of G's. I just want to say that this two-dimensional construction is a two-dimensional analog of the construction that I explained. It was in the very, very beginning. Here, we have some O's, we have some G's, and here we have DT's. So when we expanded, we get correlators of O's, G's, and we integrated over configuration space. So this has a nice analog. And again, I'll take omega I, omega epsilon on the cycle Ci. So I'll get numbers n C1, Ck. They have interesting geometrical meaning. Number of holomorphic maps passing through cycle C1, Ck. And these numbers, so people knew that such numbers exist, but it was impossible to compute these numbers. Computation of these numbers was a very hard problem in algebraic geometry. However, Kontsevich and Manin wrote equations for these numbers. Generalizing equations that I wrote to you. And all numbers, okay, not in all cases, and in many cases, all numbers were computed. And this was another Fields Prize in mathematics. Another interesting application. What if we go to dimension 4? So first equation was dx over dt was v of x. Second equation was d bar of x was 0. So it was dimension of QFT equals 1. It is dimension of QFT equals 2. So is it possible to write down something in dimension of QFT equals 4? And the answer is surprisingly yes. Here we should study gauge theory and equations are F equals F dual. And this is known as the Donaldson theory. And corresponding functional integral is plus fermions that turns out to be n equals 2 super Young-Mills theory. And this theory may be studied by tools of quantum field theory and also by tools of pure mathematics. In particular, conjecture on M theory may be checked in the study of this theory. And this is a remarkable thing. And it's another Fields Prize. However, analogs of equation NAB of tau and BC of tau was not found yet. However, we are working on it. Okay, so this is to give you perspective. Now, I also promised you idea. How to get quadratic relation. From the property of being higher topological quantum field theory, we may show that this object before being integrated over configuration space is a closed differential form. So idea, integral over closed differential form over a boundary is zero. So we integrate over a boundary of configurations. Now, what is the boundary? We have points and time intervals like T1, T2, etc. So probably here it's an interval like plus infinity, another interval like plus infinity. Boundary corresponds to some time interval going to infinity. In terms of picture, it is like this. So this interval, T, is going to infinity. So boundary looks like this. And the contribution of the boundary of the component of the boundary is a product of integrals over configuration spaces. With smaller number of points. If we combine all components, we will get equations like that's how it goes. Tim,
Yes.
is the idea clear? Probably I need to provide more details.
Mm. But how is the boundary connected with these contours C1, C2, etc.?
So here I have, so it's a boundary in configuration space.
Ah, it's like an internal.
Yes, it's a boundary in configuration space.
Ah, that's right. Yes.
You see, there are too many differential forms involved, but what can I do? I am integrating over a boundary of configuration space.
Okay.
So now I kind of advertise these quadratic relations, right? How good they are, how important they are in mathematics. And tomorrow I will provide more detail. So any questions?
Well, I have a very general question, and
Yes.
it might have been answered before, but either I missed it or got. But so are there any tractable physical applications of these topological theories? So I understand how it can be applied to enumerative geometrical problems, but
It's a good question, and answer is yes, because because these higher topological theories are nothing but supersymmetric quantum field theories. And what are you doing? You take supersymmetric quantum field theory and you consider special correlators, not all correlators. It's very interesting question how to study all correlators. But you may consider special correlators. And these special correlators satisfy interesting equations. So it is a kind of topology of supersymmetric quantum field theory. In this way, you can find exact statements about supersymmetric quantum field theory. And sometimes they are interesting. Okay. So see you tomorrow.